Okay, everybody, good morning. Even though you have a substitute today, hooray, you're still stuck with Mrs. Muser. Woo! So, I hope everything's going okay for everybody today. I am at the University of Minnesota for a calculus conference all day for our CIS stuff. So, we still do the notes like this, and let's see how it goes. So, today we work on differentiation formulas. Keep in mind, we talked yesterday about the fact that differentiation means you can take a derivative. So if we change the word a little bit, you can think of this as just simply derivative formulas. But you also know that another word for formulas is rules. And so we could think of these as derivative rules that we're doing today. And if you change the emphasis a little bit, it becomes derivatives rule. I got you. Did some of you write that down? I gotcha. Okay, so what we're doing today specifically is shortcuts. And shortcuts make us happy. So this is a happy day of notes, and I really wish I was there in person because this is kind of some fun stuff. So let's go ahead and start talking about how we can do these shortcut rules. And what we're starting with is this first one. There are 5, and there's more. We're only going to do these first 5 today, and that's going to be good, and then we can continue next week with the rest. So we're using the Leibniz notation, so let me make sure to point this out really nice and clear. This business, this d over dx, is saying take the derivative of whatever you have in parentheses. So in parentheses we have c. In other words, we're working with a function y equals c, some constant. So that means I can pick a number like, say, 4. If y is equal to 4, graphically, the function 4 is just simply a horizontal line up 4. So what would the value of the derivative be? In other words, what's the slope of the tangent line? And if the function itself is a horizontal line, then the slope of it would clearly be 0. So the derivative of any constant, anytime you have a constant term, will always be 0. Now this next one is kind of a happy one because we actually have a word for it. It's called a title. It's called the power rule. We use it so often that we might as well call it by what it is, which is the power rule. And the power rule says if you have x raised to some power, so let's say, for example, I have y equals x raised to the 5th power. What I can do to take the derivative of that is I can take the exponent, take the power, and swing it in front as a multiplier. And then my old exponent of n goes down by 1. So it becomes n minus 1. In other words, for our little specific example off to the right here, the derivative of x to the 5, if you swing the 5 in front and then go down a power, it would become 5x to the 4. So now, look, we don't have to FOIL things out. This isn't the limit as h approaches 0 of f of x plus h minus f of x all over h. Look at how short this is now. Yay! The next one is a cool little guy, and this is probably our favorite. And I'm going to tell you that it's your favorite because you don't necessarily know it yet, but you'll see it here soon. The function e to the x, remember e is a constant like pi. Pi is 3.14, e is like 2.72. And if you have e to the x, that's exponential growth. And what happens is that if you take the derivative at any point on the curve, you get, the slope of the tangent line, the next slope of the tangent line, the next slope of the tangent line. What happens is that the slope of the tangent line is the exact same value as the curve itself, which is completely creepy. And that means that the derivative of e to the x is itself. Ooh. In other words, if you accidentally just forget to take the derivative and you just copy the problem down, then you're going to get it right. Because the derivative of e to the x is e to the x. It's its own derivative. That's the only function that exists that does that, by the way, so that's why it's kind of cool. The next one is a one that I think you guys would be logically reasoning your way through anyways. So like a quick example off to the side, if I had something like y equals x raised to the 5th plus, let's say, 4x raised to the 7th. If I have to find the derivative, what I'm going to do is find the derivative of them separate and then add their answers. In other words, the derivative of f of x plus g of x is f prime of x plus g prime of x. So just to make sure we can all do this problem easily, the derivative of x to the 5th, if you use the power rule, swing the 5 in front, you get 5x to the 4th. And on the next one, if you swing the power in front, the power of 7 is in front by the 4, and so you multiply them together and you get 28. And then x drops down a power to 6. So just make sure that you understand what to do, just in case there happens to be a constant multiplier in front of a power rule already. You just multiply them together. And then I don't even know if the last one is worthy of having its own title or not. You just subtract them. So this would just be f prime of x minus g prime of x. Just like we find the derivatives and add their pieces together, we can also find the derivative and subtract their pieces. So at this point, Mr. Anderson, would you go ahead and hand out the blue worksheet? And the blue worksheet, everybody, has 52 derivatives on it. We are gearing up for a gateway quiz. And the gateway quiz, you have to score 80% or better. Otherwise, you're not going to pass the class. So if you don't get 80% the first time, you do it again and again until you get it. So I want you guys to get 80% the first try, obviously. So as extra practice problems, and these are not your homework assignments, but sometimes people want to really practice them enough so that they know what they're doing. And here's some extra ones. At this point, based on the rules that we just discussed, here's the problems that you would be capable of doing is 1 through 9, 25 through 30, and then 43 through 48. By the time we finish off our notes, like Monday next week, you'll be able to do any of those 52. So let's practice a few. So I want to start by practicing problem number 7. So as just, additional practice example problems, let's go ahead and copy down number 7. It says y of t is equal to 6t to the negative 9 plus 9e to the negative 6. There's some tricky little things that come up. So if we're using this notation, I'm going to go ahead and say that the derivative of y of t is y prime of t. It doesn't matter that it's t versus x. You still do it the same way. Go ahead and swing the power in front. So negative 9 times 6 would give you a negative 54. T drops down a power from negative 9 to negative 10. And then the next piece is what trips people up. Because when you see, and I'm going to go ahead and circle this, when people see the e, you think that the derivative of that is itself, but it's only when it's e to a variable, e to the x. If it's e to a power, remember e is like 2.72. So that's like 2.72 raised to the negative 6, which is just another number. And then you times that by 9, and that's just another number. And the derivative, and that means that's a constant, and the derivative of that would just be simply 0. I do want to point one thing out to you guys, though, is that when you find these answers, negative 54 t to the negative 10, I would like for you to get in the habit of rewriting that as negative 54 over t to the positive 10. Take this little t to the negative 10 portion and put it in the denominator as a positive exponent. That is a skill that we're going to be practicing an awful lot by using positive exponents and negative exponents and swinging denominators into the numerator and that kind of thing. So toggle back and forth between those, and that's going to be a useful tool. So let's get a little bit more practice with the whole fraction thing by doing number 8. Number 8 says r of x is equal to the square root of 10 over x to the 7th. Before we take any kind of derivative on that, I want to rewrite that. So I'm not even going to write another line. I'm not going to go any further. I'm just going to rewrite this as the square root of 10 times x raised to the negative 7. Again, take that positive power in a denominator, swing it to the numerator, and make it a negative power. And then we can go ahead and now take the derivative using our, of course, power rule. Notice how I'm careful that now I'm writing r prime, the prime standing for the derivative. Swing the negative 7 in front, and you'll have negative 7 times the square root of 10. X goes down 1 to a power now of negative 8. My final answer on this will be negative 7 radical 10 divided by x raised to the 8th power. Again, toggle back and forth between those negative exponents and putting it in the denominator as a positive exponent. Okay? A couple more examples I want to go through with you guys has something to do with some of those radicals. So if you could scroll down on the blue sheet to number 29, that's the next one I'd like to go through. 29 says s equals the square root of t, parentheses, t cubed minus root t plus 1. And anytime you have a root, so we talked about fractions, now let's talk about roots and coping with them. Get rid of them. Rewrite them as an exponent, as a power, because then we can use the power rule on them and it's easier. So as I'm rewriting, I'm just writing s equals, the square root of t is the same thing as t to the half, parentheses t to the third, minus t to the half plus 1. And get rid of your parentheses. Go ahead and distribute. And when you distribute, remember, I'm still writing s. I am not doing any kind of s prime yet. So t to the half times t to the third, remembering your old rules of exponents, you add those powers together and you would get t to the 3.5, which is also known as 7/2. On the next one, you're going to have a minus t to the half times t to the half. If you add exponents, you get t to the 1 plus t to the half times 1 is just t to the half. Now we're at a point where we've rewritten the original equation in terms of something that we can just use a power rule on. So go ahead and power rule it up. Swing the 7/2 in front. Subtract 1. So again, off to the side, think about this. 7/2 minus 1 is the same thing as minusing 2/2. So 7/2 minus 2/2, of course, gives you 5/2. Minus the derivative of t to the 1. Again, I'm going to show you the long way to write out the power rule. Swing the power in front, and it would be t goes down to a 0. And we know what's that's going to turn into momentarily. And then we finish off our derivative, which is 1/2. T to the a half minus a 1 would give you a negative 1/2. Again, since you have that negative 1/2, I'm going to go ahead and write my final answer as 7/2 t to the 5/2. The exponent of 5/2 you could write as the square root of t to the 5th, or you can just leave it. I'm okay either way. The next part, t to the 0, is nothing. It's equal to 1, right? So negative 1 times 1 would just give you a negative 1 or minus 1. And then on the next part, I'm going to be clever about what I write down here. I know that t to the negative half really goes in the denominator, but since I already have a fraction, I have a denominator of 2. So that means t to the negative half goes into the denominator as t to the positive half, and t to the positive half, I can put it back as a square root. So that would be my final answer derivative for number 29. And it is so nice that we don't have to do those the long way anymore. Now we get to use the shortcut. Be prepared for the long way in terms of like a quiz question or a common exam, but as far as the homework goes from here on out, we're going to go ahead and use shortcuts. Last example I want to do with you guys is number 48. Y equals x squared parentheses x plus 5 plus 1 over x. And just like our previous problem, there's no radicals and there's no craziness to go through, but you do need to distribute before you begin any part of the problem. So get rid of your parentheses and rewrite y. Notice it's not y prime yet, so you're just rewriting y. X squared times x gives you x cubed. X squared times 5 gives you a plus 5x squared. And here's the really good part. X squared times 1 over x makes a plain and simple x. Now we can go ahead and use our power rule and finish it. The y prime now, careful that you're writing y prime, is 3x squared plus 10x plus the derivative of x to the 1. Remember, you swing the 1 in front, and then x would go down to the 0, so I'm just going to write plus 1. And that's that derivative. And I hope this helps you, because tonight's homework should go really fast, and it shouldn't take nearly as much paper as our previous homework assignments have, because you're using these shortcuts. Yay! So let's go ahead and do the last kind of problem that you guys are going to need, which is a few application sorts of problems. So there's two. And these two application problems, you can read this one. It says, give the points on the curve where the tangent line is horizontal. So we have to be able to sort through the verbiage and decide what that means to us in terms of what we do with a derivative. So first, it's referencing a tangent line. And we know that if you're talking about a tangent line, that the derivative means the slope of it. The slope of the tangent line is the derivative. So if I got to do anything with a tangent line, I'm going to start by finding the derivative. And now the derivative doesn't take me nearly as long as it used to. Go ahead and swing this 3 in front. 3 times 8/3 gives you 8. X would drop down to a power of 2. Plus the next one, swing the 2 in front. 2 times 13 gives you 26. X would drop down to a power of 1, so I'm not going to write that. Plus, keep in mind this next term is 15x to the 1, so if I swing the 1 in front, I'll get a 15. X would drop down to a power of 0, and I'm not going to write 15x to the 0, because x to the 0 makes 1, so I'm just going to write 15. And then the last piece is minus 2. And what's the derivative of any constant? Yeah, it's 0. So we don't have to write that. And now that we've gotten the derivative, we got to figure out what to do with it. So here's the next part. It's talking about the tangent line being horizontal. So that has another special meaning to us. And if the tangent line is horizontal, that means its slope is 0. In other words, the derivative is 0. So we set the derivative equal to 0 and solve. And we can solve by factoring. Factoring on this one's a little bit creepy because it's 8x squared and not just x squared. But the first terms most people think about is 4x times 2x to multiply together to make 8x squared. And then if you have multiples of 15, that when times by 4 and times by 2, they add to give you a middle term of 26. I believe if I put a 3 here and a 5 here, that should do the trick, because then my outer terms would give me 20x and my inner terms would give me 6x, and there's the 26x. Once you've gotten that, you can say that your solution for x is negative 3/4 and your other solution for x is negative 5/2. But here is what happens on these problems, you guys. It's easy to get lost in the problem because we've done a lot of work. So now go back and say, have I answered the question? And you haven't, because the problem said give the points on the curve. So if you have to give the points, that means you need the full ordered pair. So if x is negative 3/4, you need to know the y value. And if x is also negative 5/2, you need to know that y value as well. And because I'm recording the notes, I'm just going to leave that blank. So you guys could type those into the table on your calculator, do the ask feature and type in negative 3/4 and negative 5/2, and then you could get those y values. I'm not too concerned about that, but make sure that you know that if this is asked in a quiz, that you give, like, say, the full ordered pair. Don't just give me the x value. Okay? And then next, our last example problem is using the term normal. So you'll have examples, you'll have problems that say something like, find the equations of the tangent and normal lines to the curve at y equals x root x at the ordered pair 1, 1. So the first thing I need to share with you is that when you're talking about the term normal, that means perpendicular to the tangent line. So perpendicular to the tangent line is something we can work with because we know the slope of the tangent line. So the slope of the normal line would be the opposite reciprocal. So we can go ahead and set ourselves up for success here and say that we have two lines, the tangent line and the normal line. And we're going to use the point slope form for both. So that would be y minus 1 equals m parentheses x minus 1. And that would be the same setup for point slope form on both equations, the tangent and the normal. And the only thing that's missing is m. And we know that m means slope, and slope means derivative. So before we do anything on this, I'm going to go ahead and rewrite my y equation, because if y is equal to x times the square root of x, I know the square root of x is x to the half. And the first x is x to the first. So that means when I add those exponents, I get x to the 3/2. So now we can clearly, easily find y prime by using, again, the power rule. Now you know why it's got a title, right? Because we do it so often. So that would be 3/2 x to the 1/2. Now that's the equation for the derivative. That's not the slope of our lines. So now we have to evaluate this and say at x equals 1, then y prime would be 3/2, x to the 1/2. Sorry, not x. What is x? 1. So substitute in a 1 for x. And I know that to the 1/2 is the same thing as the square root. So therefore, we get a slope of 3/2. That is the value of the slope of which line? Yep, that's the slope of the tangent line. So if the slope of the tangent line we can fill in as 3/2, that means the slope of the normal line is negative 2/3. So you just got to watch out when you're given a problem and you're told to find the normal line. You go ahead and you do the work for the tangent line, but that's not the slope you're going to use. You're going to go ahead and use the opposite reciprocal. So that's not too much of a big stretch, but you just have to know that the term normal is referring to the opposite reciprocal. And that's all I've got for notes for you guys. Here's the answers to the evens. Take a moment to look through those. You are welcome to work with each other for the rest of the class period and get your way through some of these homework problems. See what you can get done. It's the weekend, so let's get things going. If you're working with each other, that's fine, but make sure that you're keeping it to calculus work and not just hanging out because, it's Friday and it's nice and whatever. Get some calculus work done so that maybe Mr. Anderson doesn't have to write your name down or something like that. All right, you guys have a great weekend, and we will see you on Monday. Bye.